Uh, okay, so we are starting on a new topic today. So I think it's good for those rejoining today as well. Yeah. So there are some people still who are either coming in or just about. Okay. Yeah. Um, the last few lectures were spent in discussing the compactness theorem. And its important consequence, namely this. Now, the what is the content of the remark? If alpha is a consequence of gamma, then there is a finite subset of assumptions such that alpha is a consequence of gamma naught. So this in some sense was the main reason while we were doing all this. If you remember, this was our main motivation. We started looking at the consequence relation, and a priori this is very reasonable, and but it's not easy to prove, and that's what took us a bit of time to do. Yeah. So finally we could actually establish this. Now, if you recall, when this came up, uh, when I first presented this, Vikram asked the question, yeah, I mean, alpha is a consequence of some finite subset of gamma, but which finite subset? Now, that's actually a good question and an important question. And what should be clear is that after having gone through the proof, all we can say is no idea whatsoever, right? I mean, we went through a very long and detailed proof. We did a very nice construction. So we know that there exists such a subset. No idea which one it is. And now that is a kind of unsatisfactory state of affairs. After all, the whole point about attaching so much importance to that assertion is that it gives us a feeling of, some very good feeling that, there is look at what this says. There is an implicitly infinite quantification there, right? It says take any model. So it's a quantification over the class of all models, and you are saying if a model satisfies all the assumptions, all the formulas in gamma, then it must satisfy alpha. Now, if you had only finitely many, then assumptions you can at least bring it down and try to analyze. So this is precisely the sort of thing that Hilbert was interested in. And now implicitly the consequence relation is something that's infinitary. Now can we replace it with something where it's finitary and where an answer like this is immediate? So this is today's lecture. I think it's important for a different reason, is that it brings in a style. I've written proof systems Hilbert style, and we have an opportunity to discuss something by none less than David Hilbert and the way he thought. The Hilbert program that I talked about. Right? So when you have a problem like this, how do you mathematize something like this, right? So when you have a problem like this and you have no idea how to answer this, one fantastic technique you've got is to say, okay, I will come up with a new relation which, because it's written this way, let me write this way. A new relation between sets of formulas and single formulas, right? Such that define in such a way that by diktat, if then okay. So start the other way. Define a relation in such a way that if alpha is a consequence of gamma in this sense, then alpha is a consequence of a finite subset, and that follows by diktat, and by definition trivially you should be able to know which ones as well. What's the advantage of doing this? I mean, this is what is the relation of interest. What's the point in coming up with a relation which is artificial, but it has the property that you want? The idea is that you come up with this and then hope, prove that these two relations are actually the same. Then there is hope, right? Because if you have managed to prove this, then if alpha is a logical consequence of gamma, then alpha is actually a consequence of gamma in the sense that I want, and then I can go and find out which. Yeah, that would give a very precise answer to the question that Vikram asked, right? Now, is there a way? So you turn the problem. I don't know how to solve this problem. So you turn it around to say, okay, I will define a relation for which this is easy to prove, and then clearly this is not going to be easy, right? Obviously, since somewhere the difficulty must come, but and this is really Hilbert's beauty, right? And for that, you don't have to look around for a relation that you have to define artificially. This is indeed the relation that people have thought about in logic forever and ever. In fact, whatever people have been calling logic, but the very first time when I asked, what do you think is logic? This is what everybody said. And that is the notion of deductive consequence. Alpha is a deductive consequence of gamma, or gamma single turnstile alpha to denote there is a proof of alpha from gamma. Yeah, so this is the idea. And of course, if there is a proof, well, what's a proof? Proof is some finite object, right? If you're going to give me a proof, you're going to write down and give me a proof, right? That's a finite object. So the moment you write a proof of alpha from gamma, I can look into your proof, find out which assumptions from gamma you use in the proof, and I will know immediately that there is not only there is a finite subset, I will know which immediately. I just have to examine the proof. One pass down the proof and I know exactly what it is. Is the idea clear? So what does this then mean? This means that I want a proof system, a system in which I can do proofs which completely captures the logical consequence relation. If you want to hope to prove this, what is it that we need to prove? We need to prove this. If ever I can do a proof of alpha from gamma, then alpha is indeed a logical consequence of gamma. We need to prove this. So, and then we need to prove if alpha is a consequence of gamma, there exists a proof of alpha from gamma. I can actually write down a proof, right? And now, and Hilbert's argument was, after all, how do you ever establish that alpha is a consequence of gamma? right? This one, how do you ever, maybe gamma is the axioms of some particular, some particular category theory, right? And I want to show that this is a consequence. This particular statement is a theorem in that theory, right? That it's true for all models, for all the class of models that is of interest to me. How do you do that? I write down a proof and show to my fellow mathematicians, right? After all, that's exactly how I show. Now, what is the understanding between you and me when I give you a proof and you read the proof and follow what I am saying? Precisely this, that from the proof of alpha from gamma, you are actually convinced that alpha is a logical consequence of gamma. I am convincing you that indeed, take any model that satisfies all of these, it's using a finite object, right? And this was the essence of Hilbert's program, right? So now the question is, this is something that you do routinely, in some sense this is what all mathematical communication is about. By writing down a proof and showing you, in fact I even illuminate the assumptions, right? In fact, by reading the proof, you find out which assumptions I have actually used. In fact, this is routine practice, right? I hope you do that also. When you read a proof, you actually go through the logic of the thing step by step, try to follow what it says, and then you say, this assumption has been used, this assumption has been used. That assumption which was there is irrelevant because it's never used in the proof, right? This is precisely the argument that you're talking about. You walk down, proof is a finite object, at the end of which you find out which are the finitely many assumptions that you made use of. And at the end you are convinced that alpha is indeed a logical consequence of gamma. So this is the direction that you normally follow. What about this direction? That is what Hilbert really told us mathematical logic is about. You must come up with a deductive system, you must come up with a proof system in which people can do proofs in such a way that whenever alpha is a consequence of gamma, you should be able to establish that alpha, there is actually a proof. Such a proof exists. Now, as far as Hilbert was concerned, it's good enough to say such a proof exists. Then a clever enough mathematician will actually find the proof and write it down. Now, you may question that, but this is a good enough thing as far as he was concerned, because once a proof exists, a proof is a finitary object, in fact, then you don't have to worry about at all. You can cheerfully live in that world knowing that there is always somebody who can actually demonstrate a finitary proof. So everything is on finitary basis. This was his main idea. So you replace the complicated notion. Remember that this was in the early 20th century. All those Cantor's infinities were floating around. There were, arbitrary cardinalities. It was a mess. And so his idea was, once you have proved this, if and only if you know that everything can be given a finitary explanation, and that's enough. You don't have to worry about this. You can cheerfully keep doing this without worrying about the infinities that are there, because they can always be expressed. So, what is the idea of this relation? So, is the idea clear? So, the program is really to answer that question, that if alpha is a consequence of gamma, then it's a consequence of finite set of assumptions, and do it by diktat. Give a definition of the relation in such a way that the moment you write down the definition, it's obvious to you what we are talking about. The answer to that is completely obvious, and it is, as you will see. Right? But then you transfer the burden to these two things. This is usually called soundness, and this is usually called completeness. Soundness, because you are saying if I write down a proof, the proof actually does the job it's supposed to do, right? It's a sound argument, right? This is the word that we use. Completeness, because if there is it's a consequence at all, there exists a proof, right? In some sense, this you might call proof search. You are saying that there exists a proof that you can always write down. So this is the program. Is the idea clear? Any questions related to this? Okay. Yeah. So what is this definition? So this turnstile relation that we are defining is the idea of a proof system. What's a proof system for Hilbert? So proof systems, Hilbert style, I said, and that's a term that I'm going to use throughout. Talk about Hilbert style proof systems to point out that there are other kind of proof systems as well, right? And traditionally, this has been the purpose of logic, right? You write proofs, you write deductions, right? So this is the notion of deductive consequence. So this is read as alpha is a deductive consequence of alpha gamma from the set of assumptions. And I prefer this. They usually say there is a proof of alpha from gamma. And what does that mean? A proof. So first you need a system. So this thing is not written like this. It's parameterized by a system, a proof system, and proof system we denote H for Hilbert as opposed to other proof systems. So what's a proof system? A proof system consists of two categories of things. Axioms and inference rules, right? And this is exactly what you have been calling a proof all your life, right? There are certain axioms and you are allowed to follow some inference rules, right? What are the kind of inference rules that you are used to? Substitute equals for equals, right? Have an equation, right? And I make a substitution on the left hand side, I make a substitution on the right hand side, reduce the equation, right? Keep on doing reductions until you come up with LHS equals RHS. That's a proof principle. That's an inference rule. Another classic inference rule is this. What is this? If you have proved alpha, and if you have proved alpha implies beta, then you can prove beta, right? Obvious, because this is the meaning of implication for us, that if I have proved alpha as a theorem, if I have proved alpha implies beta as a theorem, then I can conclude beta as a theorem. And this is normally called modus ponens in Latin, and perhaps the one inference rule that ancients agreed on, right? There are inference rules that have been there. Philosophers have talked about inference rules for centuries and centuries. Quite a bit of the thing that you find in the modern mathematical literature goes back to Aristotle and Euclid and the Greeks. In India, study of inference systems go back to Nagarjuna, the Buddhist logician. Was roughly around the same time, in fact. And then later on in the first millennium, there were many logicians, the Jaina logicians who developed very elaborate systems of logic in India, the Chinese logicians who developed many inference systems, and they all fought bitterly about which rule is okay, which rule is not, etc. One rule that nobody ever objected to is this. I think this is perhaps the single rule that no philosopher raised questions on. So that's a good rule to keep up, right? But the point is that as far as Hilbert is concerned, doesn't matter. You choose your axioms, you choose your inference rules. This is a classic mathematician's way of thinking about it, right? You pick your poison, right? Who cares? You think this rule is bad, that rule is good, use it. These axioms are good, those axioms are bad, okay, keep whatever you want. But the moment you have got some axioms and inference rules, you have a proof system. That's the idea. That is the idea of a proof system, right? Once you have a proof system, there is a notion of a proof that you can write down within that system, and that's what we are saying. There is a proof of alpha, there is a H proof of alpha from gamma. That is a proof as allowed by H, right? Your system allows, so what is the idea of this? Axioms are assumptions you can use anytime. Inference rules tell you if I have derived this, if I have derived this, I can derive this, right? That's all there is. So formally what are axioms? Axioms simply a set of formulas. That's all. As far as the Hilbert style is concerned, you pick which your assumptions are. I don't care, right? It's just a set of formulas. Finite set of formulas, infinite set of formulas, your problem. How many axioms? Normally, in any system, any theory that you are arguing, right? Any theory you are building, you will have finitely many axioms, right? But as I said, it's your problem. Choose a set of formulas as your axioms. What is inference rules? A finite inference rules are a finite set of relations each rule is a relation because above the line you have certain, these are usually called premises, and this is called a conclusion. So what is this? This is a relation which is of the form Ri is of the form delta I alpha I, right? Where delta I is a set of formulas and this is a formula. That's all it is. These are all the premises and this is the conclusion. Is it clear? That's what it is. Now, of course, I have to say how and these premises, should they be finite or infinite, and that is Hilbert's thing. You will call this whole system finitary if the set of axioms is finite and there are finitely many relations, each using only finitely many premises. This idea of a proof system doesn't dictate that. If you want a finitary proof system, you insist that there are finitely many axioms. Every inference rule is finitary in the sense that it has only finitely many premises and then a single conclusion from this. Is the idea clear? This is just a formal signature of this. We still have to say, populate it with axioms, write down things and so on. Yeah. And so what is a proof? When do you say there is a proof? A proof of alpha in H, in the system H, from gamma is, what is a proof? How do you define a proof? So if you write down a proof and show me, how will the proof look? Finally, your proof of alpha, right? So alpha is a theorem that you are proving, right? So you will start with something and go on writing down some sequence of statements, and at the end you will write alpha and then you will say QED, right? To say I have finished the proof, right? So what is this? Is simply a finite sequence of formulas beta 1 through beta m greater than or equal to m greater than 0. Yeah, maybe I'll write it here. Such that, is it clear? It's simply a finite sequence of formulas. What else is it? A proof is step by step you are writing down something, right? First condition is beta m equals alpha, yeah, because you are trying to show that alpha is a consequence, right? You are trying to prove alpha. So the last element of your sequence better be alpha. That's clear, right? And then 2, for all I 1 less than or equal to less than or equal to m. Yeah. what are the conditions on the things that you can write down? So what are the statements you can write down in a proof? Yes. In general, if you are writing a proof, your proof is a sequence of formulas in your language, whatever language you are writing in, right? It's a, you are discussing the theory of groups. Well, you have chosen particular action symbol for that. So you're writing formulas in the language of groups, right? If you're talking about something about fields, you are working with the language of fields. You're writing statements on that, right? You remember I kept saying that we were talking about the language of statements. When we get to the language of proofs, we will have something. Now we have got all these the elements to talk about proofs, right? So what are the things that you are allowed to write down in proofs? As I said, usually you write all sorts of things like clearly, obviously, it follows from that, etc., etc. I'm going to say that that's all not relevant. Okay, yeah, you can throw away all these adjectives. All that matters is I should be able to know when I am making an assumption, right? When I am making use of an assumption, when I am referring to an axiom, right? The axiom of my theory, right? So these are things that are important for me, and what rule I am using at any point of time, and that's all. So beta I belongs to gamma. You can always use an assumption in your proof because you made that set of assumptions, right? So you can say by assumption 32, this follows, right? Remember, that's how we write our proofs. Or beta I is an axiom. Again, you can always refer to an axiom, right? Because it's an axiom of the theory, right? You are working with abelian groups, the commutativity property is there on the house, so you can say since this is abelian, right, by commutativity axiom, by whatever existence of identity, right, whatever property that you've got. Remember, these two are different things. Gamma is something, it may be a local assumption, right? You are talking about the particular, for instance, suppose you are talking about the language of fields, right? So the field axioms are always there as axioms. You are talking about a particular class of fields of characteristic P or something like that, right? So certain assumptions that you have made about the particular class of interest, right? So just to separate out all these things, right? And or what else can you do? Well, that's all you can do. Of course, you can always refer to things that you have previously derived, right? Or there exists an inference rule an IR which is of the form delta 1 delta k beta I, where for, let me not write it formally here, for all j delta j, okay, I should really write this as where all ji are less than jl, for all l 1 less than l less than k, jl is less than l. So what is it that I am saying? Look at this a little carefully. Beta I is what I am now talking about. You are allowed to write beta I if there is an inference rule for which all the premises that you have got have already been derived for you. So that means beta j1, the first premise, j1 is strictly less than I, j2 is strictly less than I. So if you have already, all the premises that you want are already there in your proof. Oops. The connection is gone. Sorry, the connection went. Can you hear me now? Yes. Okay. Yeah, there is some problem. Okay. So where was I? I was explaining this. So you are in your proof, you are allowed to always quote an assumption, or you can quote an axiom, or you can cite an inference rule and say, hey, this inference rule wants you to have these two things already derived. Alpha should occur as, so for instance, this is this, let me call beta 5, right, and this is beta 2 and this is beta 4, right. What does that mean? In my sequence, the second statement was this, the fourth statement was this, therefore now I can write this down as the fifth statement. The idea clear? You march down the proof, check that all the premises have already been derived, then you can write whatever is the conclusion as your next step. So if you are thinking of writing down a proof, how do you start? The first statement can only be an assumption or an axiom. The second statement can use an inference rule. If you had an inference rule of the form, from this you can derive this. Write down. Maybe you can put together several assumptions, this assumption, that axiom, and then derive something. Now you can use this to derive something else along with other assumptions and so on, right. This is the idea of a proof, and that's it. So once again, you say that there is a proof of alpha from gamma, right, if there is a finite sequence of statements, finite sequence of formulas, such that each alpha, each formula that you write down in the proof is either, the last one has to be alpha, each of them is either an assumption or an axiom or an inference rule, right, or basically you have used an inference rule, right, to arrive at it. This is it. And once you have a system like this, then you can make derivations, you can write proofs, and that's it. So this is the idea. Now which axioms, which inference rules, as I said, that's really entirely up to you. Now there are certain inference rules which we talked about as we went along. One of the inference rules I mentioned in the last class was generalization from constants, right. If I can derive alpha with x substituted by c, where c is a constant not occurring anywhere in gamma or alpha, then from gamma I can derive for all x alpha, right. Now this is something we showed, in fact I put it as an exercise in the assignment as well. This is something that we can prove from the semantics for the consequence relation. Now you can have that as an inference rule, right, you can have it as an inference rule which is of the form if you have derived this where c is new, then you can derive for all x alpha. That can be, for instance, an inference rule, right. So you write whatever inference rules you want, but of course the burden of the, I mean, why do you do this? Finally you have to prove that this singleton style relation finally turns out to be the same as, remember, soundness and completeness we have to prove. So the entire Hilbert project then becomes, so is this definition clear? This is the definition of a proof, existence of a proof, and how you write the proof. Now from the definition it should be obvious that this is trivial. Why? From the definition, I claim that this statement is completely trivial for this relation. Suppose there is a proof of alpha from gamma. Then the claim is that there is a finite set of assumptions such that there is a proof of alpha from that finite set of assumptions. Why is that? Well, suppose there is a proof of alpha from gamma, that is beta 1 through beta m, right? Now march down beta through to beta m, mark exactly those assumptions that from gamma that you have used. How many assumptions from gamma you could have used in this? M at most, right? Just collect them, that is your finite subset. So you do not have to just say this, you can also answer which. Just one pass down the proof and you know exactly which assumptions you made use of. The rest are, you have quoted axioms, you have applied inference rules, who cares? Because for this proof as well, I just write down those, and it is in fact that proof that beta 1 through beta m is in fact a proof of alpha from gamma naught. Yeah. Is this clear? So this is what we wanted to do, and that is why I said this is by diktat that this follows. What about other properties, right? Monotonicity. That is, if and this is obvious. Why? Suppose there is a proof of alpha from gamma, right? And I take a larger set of assumptions. What is the proof of alpha from gamma prime? Same proof. It is just that I never use the other assumptions, right? The identical proof will be the witness for me. So several of the properties and things that I was talking about actually come very straightforwardly from here. Not all, but we will see more. So this is the Hilbert project, right? The real thing that you want to study, as I said, the hero of our course is the double turnstile relation, the logical consequence thing, right? But here is a means for studying that relation, right? Rather than taking a complicated relation and talk about its properties, you replace it by this, and then of course you have to prove. So the entire project is so for first order logic, come up with suitable axioms and inference rules such that is the idea clear? Because the moment you have written down your axioms and inference rules, this relation is defined and we have to prove this relation we already have defined. So we just have to prove that these two. So it is not that you first write down some axiom and inference rules and then ask, oh, have we got it? No, you come up with appropriate rules so that we can prove this. This is the idea, right? The properties that we want of the consequence relation are obvious, right? So that is not a problem. You just have to make sure that this is not some arbitrary relation, but actually corresponds to the relation of interest. Any question related to this? Yeah? Okay. Yeah. So this is the idea. Now how do you come up with axioms and inference rules? Now this is an act of creativity, because you can choose law, as I said, and of course, remember Hilbert was not particularly interested in doing this for general first order logic. He was interested in coming up with, fix a particular logical language, for instance arithmetic. For arithmetic, write down axioms and inference rules, right? For the reals, for complex numbers, for geometry. I mean, Hilbert's PhD thesis was for geometry. The oldest axiom system that we know, The rigorous axiom system is Euclid's axiom system, right? For and it's just high school geometry, right? So there are, I hope you remember your parallel postulate and various postulates, right? So there are several axioms and inference rules, and you do proofs. In fact, the formal proof notion that you actually start studying is really in geometry in school, right? And Hilbert was really after that. And if you remember the first lecture that I mentioned, 1905, Hilbert and Bernays wrote a book called Grundlagen der Geometrie, where they actually did exactly this exercise for geometry. So this was not a, oh, this thing is gone again. Yeah, the connection is unstable. Okay, let me continue. So so we want to do this for particular theories, right? So by the way, can you hear me?
So the board is not clear.
Board is not clear. Is there a focus problem or?
Yeah, focus problem.
Oh, can I just check that? Just give me a moment. Some focus issue. Okay. Better now?
No, it's still out of focus.
For all or
A bit better than before, but
What about somebody else? Others also tell me. Siddharth?
Sir, it just yes, sir. Now it's better, sir.
It's better? Okay.
Yes, sir. Now it's better.
Anybody else? Lavanya, is it okay for you?
Yes, sir, it's okay for me.
Okay, fine. So I'll continue, but please tell me if there is a problem so I can stop it. Today the connection is unstable, so there may be some, it may keep going off. So, and it's not just going off, but when it comes back, it doesn't come back exactly to the same status. Well, internet, we have to live with all this. Yeah. Okay. So yeah. So this is the project. As I said, Hilbert was interested in doing this for specific theories, and those are the things that we can take up later on. But now the main question is first order logic. You have this relation, so come up with axioms and inference rules. Now, what we are going to do is we studied this relation for first order logic, and in the process, while we were doing this, I said, okay, this is becoming difficult. Let's take up throwaway quantifiers, do this. And then for equality was a problem, I said throwaway equality, let's do this, and then added things slowly, right? Now this time I'm going to follow a slightly different trajectory. I'm going to just start with propositional logic. So we don't do this exercise for first order logic, but let's do this for Boolean logic. What is propositional logic? Syntax, fix set of atomic propositions or Boolean variables, and the syntax of formulas is whatever is your class of formulas. Yeah, you just have not atomic relations, atomic predicates, whatever, you just have atomic propositions, negation, disjunction, conjunction, implication, equivalence. Yeah, that's good enough. Let's just do this exercise because we still have this thing, right? This notion is already there. What is this notion? It says for all models. What are models for propositional formulas? Assignments of zeros and ones to your propositions. Whatever Boolean variables you have got, whatever is your Boolean formulas here, you just have to assign them zeros and ones. And then you ask for every such model that makes all of these true, does it make this particular Boolean formula true, right? Still it's not clear what axioms and inference rules I can write down, right? And I thought in any case, when it comes to Boolean logic, you know the models very well, you know satisfiability, you know all that, but I don't know if you all know the notion of deductions well enough. So we might as well take up and go over it, right? So what is a Hilbert style axiom system for propositional logic? Let's see, and that let's do first, and then we'll bring in quantifiers and the full glory and do the proofs. This is to say that already the proof is fairly non-trivial. So what do we want? We want to come up with axioms and inference rules such that two things have to be proved. Remember, the soundness direction has to be proved. Completeness has to be proved. Of these, which is the easier requirement, which is the harder requirement? Well, in some sense this should be the easier requirement, because if you have written down a proof, that better be doing the right thing, right? That is correctness. We shouldn't really call it soundness, we should call it correctness. Computer scientists talking about inference systems, proof systems usually use the term correctness and completeness, because this is what correctness is about. The more classical terminology is soundness and completeness. But my point is that already the fact that we have to prove this already tells you what must your axioms be. What it already gives you conditions on the axioms and inference system. So which axioms are we going to choose? Which inference rules are we going to choose? Don't put any of them, right? Let these conditions already guide us to what axioms and inference rules you want. You understand what I mean? One good mathematical way, when there is a wide choice, right? There is a wide choice of axioms. How do you pick which ones? Well, let these are things that we need to prove, right? Let that guide you into what we should be putting them down. So let's see how that works. Okay. So yeah. Let's say this direction, this already tells you certain things. What? Suppose there is a proof of alpha from gamma. Then you have a proof like this, right? Blah blah blah. I mean, the proof you have a finite sequence ending with alpha. Now, I want to show that, right? I want to show that then to prove this is what we want, right? If there is a proof of alpha from gamma, alpha is actually a logical consequence of gamma. How do I hope to prove this? Well, whatever be that proof, right? How do I hope to prove that alpha is a consequence of gamma? Well, I have no idea about what the proof actually goes through, right? What are the steps in the proof? But one thing is very clear, that at the end of it, the last one that I write down in the proof better be a logical consequence of gamma. How do you ever hope to do such a thing? Simplest thing is to say, I don't know what is this, but there is a parameter that this gives me. This assumption gives me one parameter. What is the parameter? That is m, the length of the proof. So there is one standard trick, the natural thing to try is, let's try to do this by induction on m. This is what you call a very hopeful proof strategy. I know nothing about what is inside. I have no hope whether this thing is provable or not, but there is a strategy available to me, right? by induction on M, what do? I try to actually do this for every step here. Let's try to show that for all I suppose I can prove. So sufficient to prove for all I, beta I is a consequence of gamma. That is, every step of the proof gives me this. If I prove this, of course it holds for M as well, and then alpha is a consequence of gamma. This is very reasonable if you think about it. Okay, what is beta I? Well, beta I could be an element of gamma. If beta I belongs to gamma, of course beta is a logical consequence of gamma. It's obvious, right? So if I am using an assumption, I know that that particular assumption is already a logical consequence of gamma. So no issues, right? Okay. What about beta I is an axiom? Now this is the point. When you write down an axiom, what are you saying? This is something that holds no matter what assumptions you make, right? That is the idea of an axiom, right? This is something that holds by virtue of the theory, right? What I am working with. Therefore, what you mean is that intention is this, that beta is a valid formula. That's the idea of an axiom. An axiom means no matter what model you pick, it must make it true, right? For propositional logic, you call them tautologies, right? Something that's true. And then, of course, this implies if beta is valid, of course, beta is a logical consequence of gamma for any gamma. That's clear, right? Because take any model. Who cares about if it satisfies all the assumptions in gamma? It doesn't matter because it will satisfy beta, right? It's true in all models, therefore, of course, it's a consequence of beta. So, this already tells me that all axioms should be valid formulas. Yeah. I don't know what the axioms are going to be, but if I want soundness, I better make sure that every axiom that is there in the system better be a valid formula. Don't put in anything as axiom which is not true in all models. That seems very, very reasonable, right? That why would you put in something as an axiom that can be falsified by some model, right? So it should be something that is true in all models. Then what about this step? Suppose you have, now how did beta I come about? Beta I was either a member of gamma or is an axiom, or it was got from by application of one of the inference rules. But then my induction hypothesis applies, right? I already, by induction hypothesis, gamma beta J1 is a logical consequence of gamma, and so on. Beta Jm is a logical consequence of gamma. This is something that is true by induction hypothesis. I want to write therefore beta I. This is the same as saying that every inference rule preserves consequence. What is a necessary condition for your inference rule so that you can prove soundness? Your inference rule should be such that if you have ever written something like this, for instance, alpha implies beta, this is our modus ponens, right? That's an inference rule. We have to show that it preserves consequence. That means if alpha is a consequence of gamma, and alpha implies beta is a consequence of gamma, then beta is a consequence of gamma as well for any gamma, and that of course is true, right? Take any gamma, if yeah, take any model that makes all of gamma true, that particular model makes alpha true, that particular model makes alpha implies beta true, therefore that particular model makes beta true. So that's it. So once again, this looks like magic. There is no magic, it's just a straightforward consequence of what we want to do. If you want soundness, it better be the case that all your axioms are valid formulas and all your inference rules preserve consequence. Another way of saying is that to prove soundness, it suffices to check that all your axioms are valid and that your inference rules preserve consequence. So soundness follows from, so let me write this. So your inference system soundness of the system follows so this is done. And so this is basically what we are now trying to argue. So the important thing is completeness. That is the really hard bit of work. So which axioms, which inference rules, we have not answered. This is the important point. For soundness, for correctness, as long as you make sure that axioms are valid, inference rules preserve validity, preserve consequence, then you are sure that all your inferences are always going to be correct, right? Because this is how what you use in your proofs. Now, the choice of which axioms you use, which inference rules, is only among all the valid formulas, which valid formulas are used as axioms. Among all the potential inference rules, which inference rules shall we use as our inference rule? There are lots and lots of rules that preserve consequence. Which ones do I choose? And that is dictated by the second condition. I want completeness, right? I want to put in sufficiently many axioms, sufficiently many inference rules, so that whenever alpha is a consequence of gamma, I can actually write down a proof, right? I can actually demonstrate a proof of alpha from gamma using those axioms and inference rule. So there must be sufficiently many. On the other hand, our interest is mathematical, so we would like to have a lean and mean axiom system, right? You want to put in as few axioms as possible, as few inference rules as possible to make sure this happens. So that's really the name of the game, right? You want to come up with axioms, and as I said, this is only Boolean logic for propositional logic, right? Now, for instance, so let's look at what kind of valid formulas are there for in Boolean logic. You all know Boolean tautologies. So let's think of some. For instance, this. Yeah, definitely. If alpha and beta holds, then alpha holds, right? This is valid. This is valid. Yeah. This is simply a way of weakening the assumption, right? From alpha, you can always say alpha or beta holds. We know this is the meaning of implication. Yeah. Alpha implies beta is the same as negation alpha or beta, which is in fact equivalent to not of if alpha implies beta, you can never have the case where the assumption is true but the conclusion is false, right? And then the so called De Morgan's laws. Yeah. Any more validities? I'm sure everybody knows lots of validities, right? This equivalence itself is alpha implies beta and beta implies alpha. Yeah, that's something that. So these are all examples of potential axioms. Yeah. What else? What about examples of inference rules? That is, rules that preserve consequence. I have already written one. Any other?
Sir,
Yes.
this is alpha implies beta and not beta. You mean not alpha?
Yeah. So alpha implies beta, alpha implies not beta, not alpha. This is, I'm sorry, not, yeah, exactly. What is this? RAA? Reductio ad absurdum, right? I make an assumption alpha, from that I have come to a contradiction, therefore negation alpha holds. Normally it's used in not in this form, it's used in the following form. Not alpha implies beta, not alpha implies not beta, therefore alpha. So you want to prove alpha, you say suppose not, right? That is the same as not alpha. That from the suppose not you arrive at beta. From the suppose not you arrive at not beta also, and say, hey, this is a contradiction, and therefore our assumption of suppose not was wrong, therefore alpha holds. So this is called reductio ad absurdum, and one of the most popular inference rules that we use in mathematics. In fact, the last few lectures that I've been doing, all the time I was writing suppose not, okay. These are finitary inference rules. Do you know of any infinitary inference rules? Well, in Boolean logic you never use infinitary inference rules, but are there other, we know first order logic, right? Give me an example of an infinitary inference rule that you use all the time. What do I mean by infinitary inference rule? The thing above the line, there is an infinite set, right? Remember, inference rules by themselves don't have any assumption on how many premises you have, right? It's simply a relation between a set of formulas and a formula, right? So this is what we are used to. Do you remember this particular rule? And if you want to be fancy, you write successor of n. What is this rule? Principle of mathematical induction, right? Another thing that you grow up with, right? This is an infinitary rule. Why? This is not a formula. There is no for all n here. I mean, if you want to write it, but basically you prove this and you prove this for all n. If you can show infinitely many such premises, right? Remember that this proof you are assuming for all n, from that you conclude this, okay. Now maybe I can directly put this in, okay, there are some various questions related to this, but this is a typical example of one. But anyway, we are back to propositional logic, Boolean logic. So this is not the any other rule. What about this? Contrapositives, as it's called, right? But this is pretty much the same as reductio ad absurdum. To conclude that alpha implies beta, I start with assuming negation beta. From that I derive negation alpha. Therefore, I conclude alpha implies beta. This is something again that we use a lot. So this is proof by contrapositives, people say. But as I said, don't worry about this. The point is that through the centuries, philosophers talked about various kinds of proof rules of this kind, and they all have some merit and that you make use of or not. So the question is this: which particular ones am I going to use? Which particular ones which inference rules am I going to pick? What we would like is a lean and mean inference system, right? Something not lot of baggage, have as few rules as possible, as few axioms as possible, so that but in such a way that we do not compromise on our goal, namely to show completeness. Of course, we have to show soundness, but how do we ensure soundness? We have already seen. We will only employ valid formulas as axioms and only those that preserve consequence as inference rules, by which I know that soundness is guaranteed. So this is how we are going to do the proof. We are not going to pick some axioms and hope that you will get completeness. No. So the goal is this. Come up with, so this is going to be our goal for now. Goal, choose axioms where we remind ourselves they have to be valid, and inference rules that preserve consequence, so that we can prove So how do we choose this? And here is a trick, and I hope right in the beginning I said, right, learning logic is not about particular learning theorems or whatever, but certain tools and techniques, certain questions to ask. And one of the fundamental things I hope you will learn is a technique, and this is this. Answer is very simple: do not write down any axioms, do not write down any inference rules. Then how do you do? Start doing the proof. By the time you complete the proof, you would have added axioms. Somewhere you need some axioms, put it in. As long as it's a valid formula, you can always put it in, right? And that is a very nice technique, and this is Hilbert, is not, So okay, so let's just do that. So we have this system H, which has some axioms, some inference rules. Which ones? No idea, completely empty. I start doing the proof, and as and when the proof dictates that something is needed, I put it in. If I put it in here, I check that it's a valid formula. If I put something here, I check that it preserves consequence. In fact, I'm going to get even meaner than that. I'm going to say that, remember that one non-controversial inference rules that we had? And which we have already said preserves consequence. What I'm going to do is I'm going to use only that as the rule of inference, no other rule of inference. Okay, so it comes down to only this. Where does it give me the confidence that I can do this? Well, enough water has flowed down over these things. Philosophers had talked about not only various rules, but have shown, for instance, from this, with this, you can derive this, etc., etc. So it so happens that there is enough evidence to believe that this is possible. But you will see as we go along that there is nothing else that is needed. In fact, this is the only important thing. Okay. So which axioms, as I said, start with the empty set and start doing the proof. But how do you hope to do this proof at all? You start with the assumption that alpha is a logical consequence of gamma, and then I have to prove that alpha, give a proof of alpha from gamma. This is for any alpha, any gamma, right? For all. Now this is a fairly deadly thing. How do you hope to prove something like this, right? Now for that, now we go back to certain properties of our consequence relation. Now we know that these must be true of the proof relation as well, right? One thing that I said follows obviously is monotonicity, right? There and this, what about this? This means that alpha is valid. For this I want this. What is this? When is there a proof of alpha from the empty set of assumptions? Do you remember? Yeah, when is this? This means that there is a proof of alpha which uses only axioms and inference rules. There is nothing to refer to here, right? This means there is a proof of alpha only from in fact our only one inference rule, modus ponens, so it must be the case that so every valid formula should have a proof, right? Every tautology I should be able to derive in my system. So the axioms must make sure that every valid formula is derivable, right? This is the condition that I want. What other property that we had? Another property that we had was this. If and only if this formula was valid. Right? Everything from the left hand side you should be able to pull to the right hand side, right? If your set of assumptions was finite, alpha is a consequence of a finite set of assumptions, if and only if the conjunction of these implies alpha is valid. This is something that we saw as a property of the consequence relation. We want something like this. I'll just write it in a slightly different way. So I'll write the same thing but in a slightly different form which is more convenient. This is a property of the consequence relation. Why? If beta follows from the assumption gamma union alpha, the claim is that alpha implies beta follows from the assumption of gamma. Let's see why. Suppose this is true. To prove is this. Well, take any model that satisfies all the assumptions of gamma. To prove that the model satisfies alpha implies beta, suppose the model satisfies alpha as well. Then the model satisfies all of these, therefore it must satisfy beta. Conversely, suppose you assume this and show this. Yeah? Are you with me? I think this is frozen. Hello?
Yes, sir, it's audible.
Okay, because I think the videos have all gone off, so I can't even see anyone. Can you see the screen and whatever?
Yes, sir.
Okay,
Yes, sir.
okay, fine. Where was I? Yeah. So suppose you assume this and you want to show this, right? Consider any model that makes all of gamma and alpha true. Well, that model makes all the assumptions true, and then you can see that alpha implies beta also is true in the model. Yeah, and therefore beta holds. So this is something that's obvious, and so we would like, so we need to ensure yeah, by this property, this is something we need to ensure. So we need some axioms that will make sure that whenever this is true. Now the thing is that one direction is straightforward. Suppose gamma derives alpha implies beta, right? Then gamma union alpha also derives alpha implies beta, right? Because I can always add assumptions, nothing goes wrong. And of course gamma union alpha derives alpha, right? Because it's one of the assumptions. Therefore by modus ponens gamma union alpha derives beta. So one direction, oops, again the connection is gone. No, you can't do anything, you have to wait. Today there is a real connection problem. I'm back, but I don't know if you can see me. Okay, let me just make this point and probably we'll finish it for today. Yeah, so what I was saying was that we need to ensure this, but here this direction is trivial, completely straightforward. This direction on the other hand, that if from gamma union alpha there is a proof of beta from gamma union alpha, then there is a proof of alpha implies beta from gamma. This is sufficiently non-trivial, and this is something that we have to make sure of, and ensuring this, it turns out is something very interesting, right? So this is one important thing that we will need to do. Another important requirement that we have, so my point is that there are certain requirements that we have. What are the requirements? If alpha is valid, we want there should be a proof of alpha from the empty set of assumptions. This is one. Second is this direction that I have just written. If this is a property that holds for the consequence relation, semantic consequence relation, therefore we want this to happen. Third requirement was another property of the consequence relation, which was that if from that is, if gamma was unsatisfiable, remember alpha is the consequence for any formula alpha, right? This was a property that we talked about for the consequence relation. So we want this also. These are things that we need to make sure, otherwise the relation that we are talking about will not coincide with the consequence relation. So since the consequence relation has these properties, our deductive consequence relation also should have these properties. Okay. So now, so basically it turns out that once you have axioms that fulfill these conditions, completeness also will fall through. That is, we will be able to prove that if alpha is a consequence of gamma, I can actually demonstrate a proof of alpha from gamma. So this is something we will take up next time. Yeah, I am sorry about this breaks today, couldn't do much about it. So internet created some problems. So hopefully next time will be better. Any questions, comments, anything? So what I have done today is to introduce this idea of deductive consequence, and for at least for propositional logic, how we are going to go about trying to fulfill completeness. Soundness will follow by ensuring that all the axioms are valid and inference rules preserve consequence. Completeness we have to ensure, and that's harder, and the way we will do it is that certain properties have to be assured anyway. So what we will in fact show is that once you fulfill 2 and 3, 1 follows, exactly like we did for compactness by writing down certain conditions. Like we said, okay, finsat and complete, that does the job. How do I ensure then from finsat to finsat and complete? Then how do I ensure witness? Like that. Here, if I ensure 2 and 3, 1 follows. And then it turns out that if 2 and 3 are satisfied, you can even prove completeness, right? This is the sort of thing that we will do. Okay. So thank you.